Swayam Prabha. Digital India. Educated India.
Next, what we are going to look up is some concepts in mechanical energy. Just like force is a mathematical construct to explain displacement of bodies, energy is also a mathematical construct for an alternate formulation to explain displacement of bodies. Okay. So, basically here we are interested in looking at three concepts. One, what is called as strain energy, or stored energy. The second concept is load potential, and the third concept is total potential. Okay. There are two kinds of stored energies, one which is just called as plain strain or stored energy, and the other thing is complementary strain energy. Okay. Let us understand first what the strain energy or stored energy is. Okay. Say I have a bow and an arrow. Okay. Now, what happens when I pull this back? The string gets deformed like this, and this thing comes in here like this, right. Now, if I let go after deformation, the spring comes back here and the arrow flies off, right. So, basically what is the energy that is stored in the string because of you pulling back is released when I let the arrow go, and the strain energy is converted into a motion of the arrow. Okay. So, that is what strain energy is. It is in a sense the capacity of the body to do work, useful work. Okay. Now, how do you compute strain energy? Let us look at the uniaxial case. Okay. To compute the strain energy for uniaxial case, I have sigma versus epsilon axial stress versus axial strain. Say I had a curve, I have a straight line like this, what is typical of a material which is linearly elastic. Okay. Now, I have two options now. I can compute the area under the curve, I can compute the area under this curve, that is called as strain energy, strain or stored energy, or I can compute the complementary of it, which is this area. This is called as complementary strain energy. Okay. It is called as the complementary strain energy. Now, for a straight line there is no difference between complementary strain energy and strain energy, right, because it is a straight line, this half times delta, the area remains the same. Okay. So, on the other hand, if I add a material like rubber, this is for material like steel, other hand if I add a material like rubber, it will show some sustained response like this. It will show some sustained response like that, and then there is a difference between whether I compute this part of the energy or whether I compute this part of the energy. Okay. Now, how do you compute this area or that area? To compute the strain energy, I have to do integral sigma d epsilon, right, because I am varying epsilon here, I am varying epsilon here, this is d epsilon, and that is the value of stress at that particular point. I sum that up to get the strain energy. Similarly, to find the complementary strain energy, I have to integrate epsilon with respect to the stress, right, to integrate epsilon with respect to the stress. Now, let us do this for a uniaxial case of a linear elastic material. We know that for linear elastic material, sigma is given by lambda trace epsilon identity plus 2 mu epsilon. Okay. So, when I want to find strain energy, I have to integrate sigma with respect to d epsilon, which means I have to find sigma as a function of epsilon, which in turn will boil down to plus mu trace of epsilon square. Okay. This is the general expression for the strain energy in a linear elastic material. For a material that obeys Hooke's law. Okay. Now, let us find out what the strain energy would be for a uniaxial state of stress. Okay. Let us assume for the uniaxial experiment loading, you add strain as epsilon xx 0 0 0 epsilon yy 0 0 0 epsilon zz, right. From Hooke's law, from what we did define Young's modulus as, this will be epsilon axial 0 0 0 minus nu times epsilon axial 0 0 0 minus mu times epsilon axial from our definition of the Poisson's ratio. Okay. This is Poisson's ratio. Okay. Now, what will be u then? What is trace of epsilon? Trace of epsilon is 1 minus 2 mu epsilon axial, okay, and trace of epsilon squared would be 1 plus two mu square epsilon axial squared. Okay. So, substituting this in the expression above, we get the strain energy as lambda by 2 1 minus 2 mu squared plus mu times 1 plus 2 mu square into epsilon axial squared. Okay. Okay. So, this will be nothing but lambda by 2 into 1 plus 4 nu squared minus 4 nu plus mu times 1 plus 2 nu square epsilon axial squared Now this I can rewrite it as E by 2 epsilon axial squared, where I substitute for lambda and mu the expression from involving Young's modulus and Poisson's ratio, and I will simplify this equation to get this as Young's modulus times epsilon axial square by 2. Okay. In other words, what you have is you have to integrate, you know that sigma axial is E times epsilon axial, okay. The other components of stresses are 0. Okay. So, what will happen is this u is integral E times epsilon axial, the other components of stresses are 0. So, it will be d epsilon axial. So, this is nothing but E epsilon axial squared by 2. Okay. So, the simpler way of doing that is that the correct or the straightforward way of doing is what we did before, what we did here. Okay. Now, let us find the complementary strain energy. Which is denoted by u star, this is nothing but epsilon d sigma. Okay. For us epsilon was 1 plus nu by E sigma minus nu by E trace of sigma identity. So, this will boil down to 1 plus nu by 2 E trace of sigma squared minus mu by E trace of sigma squared by 2. Okay. So, that is the complementary strain energy. Now, for the uniaxial state of stress, for uniaxial loading, you know that sigma is sigma axial 0 0 0 0 0 0 0 0. So, trace of sigma would be sigma axial and trace of sigma squared would be sigma axial squared. So, u star would be 1 by 2 into 1 plus nu by E sigma axial squared minus mu by E sigma axial squared, which will be 1 by 2 sigma axial squared by E. Okay. So, u star is 1 by 2 E sigma axial squared. Okay. So, basically now you have found that the complement, what the complementary strain energy and the strain energy are. Now, how do you know that these are the same? Because you have the relationship between sigma axial and epsilon axial as sigma axial is E times epsilon axial. So, if I substitute in there, you will find that these two are same. That happens because the material is linearly elastic. For a non-linearly elastic material, in general the complementary strain energy and the strain energy would be different. Let us look at load potential. This is denoted by V. This is defined as negative of summation of applied force into the displacement of the dot product with the applied force. Okay. Dot product of the displacement at the point of the applied force. So, for example, if I have a body, if I have force applied F at this point and this point displaces by u of phi, then it is the work done by this force for it to displace by that distance u of phi. Okay. So, the load potential is negative of F phi dot with u of phi. Okay. That is a scalar, that is you are projecting F onto ui, that is the displacement in the direction of the applied force. Okay. Load potential is negative of displacement in the direction of the applied force. Okay. That is the load potential. Okay. Finally, the total potential is, you have to sum this from I equal to 1 to n for all the forces that you are applying. If you have F there, another F here, and this point displaces by u2, V would be F1 dot with u1 plus F2 dot with u2. Okay. Finally, the total potential is defined as pi is defined as u plus v. If I did not have a negative sign here, if I did not have a negative sign here, I would have introduced a negative sign here. Okay. So, basically that is the trade off. I introduced a negative sign there because I did not want to introduce a negative sign in the total potential. Similarly, there is a complementary total potential which is denoted by pi star, which is nothing but complementary stored energy plus the load potential V. Okay. So, basically we have seen what a strain energy is, what complementary strain energy is, what load potential is, and what total potential is, and what complementary total potential is. Okay. Now, to solve problems, just like we had 4 concepts, what we have to do is we have to minimize this potential in terms of some unknowns that yields us the solution to the boundary value problem in energy formulation. Okay. We will see more of it in the coming lectures, but just like there were some concepts that we saw in the force based formulation, the energy based formulation, the basic concepts are the strain energy or complementary strain energy, the load potential, the total potential or the complementary total potential. Okay. To solve a problem, we will minimize the potential. Okay. To get the governing equations for a given boundary value problem, we have to minimize the total potential or complementary total potential. Okay. This is in energy formulation, essentially energy formulation. Okay. With this we will conclude today's lecture. Thank you.